Hello, this is Concrete Path. Today, our topic is that the torsion of circular shaft. Torsion of circular shaft. Torsion of circular shaft. So we say that we use that circular section, circular cross section, and the shaft is formed. That is the member subjected to a torque, or we can say twisting moment. A torque or twisting moment. Twisting moment. So torsion means that twisting of the member. So torsion means that twisting of the member, twisting of the member, twisting of the member. Let's say this is your shaft, or we can say bar or shaft. Twisting of that bar when we applied torque, when torque is applied, when torque applied, and rotation about, and the member rotates about long axis, rotation about long axis. That we also call as polar axis. In this case, we also call it as a polar axis. So let's say the member rotates about the long axis. So the moment is applied in the long axis, and the member also rotates in the same way. So I say that the moment applied in the long axis direction, and similarly you have this one, what you call as a rotation about the long axis. That is twisting of the member. That is the twisting of the member. There we have pure torsion. Some with respect to that, we have the pure torsion. We say if there is only torsional moment, that means no shear force is acting. Yeah, no axial force and no bending moment is applied. No axial force or no bending moment applied. Only that torsional moment. Similar to the case of that pure bending, when we said that if there is only bending moment, so we have this diagram of BMD, and we have the shear force 0. Similarly, axial force diagram was also 0, AFD. Now for the pure torsion case, we say you're applying only torsional moment. You're applying moment, but that's in the long axis, about the long axis. So let's have that. So this is your shaft, and this is this cross section. Now somehow you installed a bracket plate here. And now you're applying a force P here, and similarly P upwards. So let's say this direction is your Z direction. This is X and this is Y. And so you applied a load. You installed the bracket plate in the Z direction, but you are applying a load, let's say in the vertical direction. This is along the Y, PY. So you developed a moment that's in the anti-clockwise direction. And if you talk about the long axis, that's along the long axis, I would say. Moment developed M because of load Y, but it's in the X direction because it's rotating in the X direction. About the X direction, it's rotating. So I say that moment X. Let's call it as M1X. Similarly, if you installed a bracket plate or a bar, let's say you installed a bar here. You installed a bar here along the vertical. Now you are applying moment. You're applying a force in the Z direction. Let's say you applied a Z force in the Z direction. Let's say the force applied in the Z direction in this way. Let's say this is P, clockwise. Let's keep the sign opposite. Let's keep the sign in the opposite direction. Let's say you applied for this now. You apply load in Z direction. Because of this, there is a moment developed that's in this way, that I can show that final, that you applied a moment M2, but about the X direction. So similarly, you applied some moment anti-clockwise, moment 1 in the X direction. So this is your final moments on the section, on the beam, on the shaft, we can say. So either you can apply loads. The loads should be applied perpendicular to that section, perpendicular to the section. Let's say this is your section. You are applying loads out of the plane, out of the plane. Let's forget that now. And from that, you can make the line diagram also. We say that we had the sign convention. Let's talk about that later. So yeah, let's talk about that sign convention now. Let's talk about that sign convention. Let's talk about that sign convention. Sign convention. We say that we have the concept that we can use that. That's called as right hand thumb rule. Right hand thumb rule. Right hand thumb rule. So use the right hand, and you see that the moment m1x, the moment m1x is in the anti-clockwise direction. So your right hand, you should rotate it in anti-clockwise direction. So moment is applied m1x in the anti-clockwise direction. It's in the anti-clockwise. But how can you show that it's in the anti-clockwise? How can you rotate your hand, right hand, that's showing that anti-clockwise rotation? This is your clockwise rotation. So this one is your anti-clockwise rotation. That means your thumb points away from that section. So your point points away from that section. When you rotate anti-clockwise, your right hand you rotate anti-clockwise. So your thumb points away from the cross section, So you can make that your thumb, we represent it by the two arrows, that this is the direction of thumb. Two arrows represent the direction of, this is the direction of thumb. We can say this is the direction of thumb. So we can write here moment m1x, moment m1x. Similarly, you are applying moment of m2x. So that's what it is. This one actually this one is your clockwise moment. If you have this one is your clockwise moment. And how can you show that anti-clockwise moment? Clockwise moment is in this way. This is in this way. So this one is not that clockwise moment. This one is your anti-clockwise moment. Let's remove this one. Let's say this is your m2x. That's clockwise moment in this direction. Actually, this one is also not the same. Clockwise moment is in this way. Let's forget this. Clockwise moment. So we have this clockwise moment. This is your moment of m2 into, let's say, moment 2 in the x direction. So this is your clockwise moment. So this is your moment m2 in the clockwise direction. So your moment is in the anti-clockwise direction. So if you rotate your right hand, in the clockwise direction, so that means your your thumb points towards the cross section. I can say in this direction. Your points in this direction. Let's take that. That means your your thumb points towards this direction. Let's say this is your moment m2x. Now you have this fixed support. So it would resist that twisting. It would resist that moments. It would resist those twisting moments. And let's say there we have developed some moment. Let's say the net value of these one is your clockwise, next one is your anti-clockwise. There would be net value m net. Let's say the m net is it is in the clockwise direction. That means your moment developed would be in the anti-clockwise fashion. Anti-clockwise. This is your anti-clockwise. M developed anti-clockwise. Let's call it as a m anti-clockwise. So if your moment is anti-clockwise, if the support develops an anti-clockwise moment, so let's say this is your anti-clockwise moment. So this was your clockwise moment. This is your anti-clockwise. That means your thumb points towards the section. Let's say in this way. You can show this arrow. So this is your m anti. So this is your, we call it as a line diagram for those twisting moments. Line diagram. Now we have the sign convention. Let's say that you applied a moment here. Let's say this was your shaft, circular shaft. you applied a moment of you applied a twisting moment or torque of T in the clockwise direction. So to balance it, there should be anti-clockwise developed from the other side. Let's say this was fixed support. So there would be, for this clockwise, there would be anti-clockwise. There would be anti-clockwise T developed. So to make the line diagram, for the first one, we say that there is a clockwise moment. So the point that thumb points towards the section. So the thumb points towards the section. Let's say this is D. And similarly, from the other side, your moment is anti-clockwise. Your moment is anti-clockwise. That means your torque is anti-clockwise. That means you have to rotate your right hand in the anti-clockwise direction. That means your thumb is pointing towards the section. Thumb is pointing towards the section. So this is your T here, and we say that if your thumb or T points towards the section, we say that T is positive. Torque applied is positive. We say that the torque applied is positive. This is your line diagram. Now to make the we call it as a torsional moment diagram, TMD. Let's make the TMD. I would say this is your positive. Positive T. Then it goes. After that, you are facing a T in the opposite direction. So it will fall down by amount of T. So this is your TMD. Now the thing is that we say because of torsion, there is development of shear stresses. We will derive that equation also. We say that if the torsion is positive, if the torque applied is positive, I would say the shear stress developed will be also positive. So if you want to say if this was your positive torque applied on the section, I would say the shear stresses developed would be positive. Positive shear stresses. Now one more thing is that if your torque is applied in the anti-clockwise direction, let's say you applied a torque in the anti-clockwise. This was your torque that you applied in the anti-clockwise direction. Now there would be balancing this a clockwise torque, twisting moment, torque. So this is your clockwise, anti-clockwise. Now to make the line diagram, I would say you are applying an anti-clockwise moment. So you rotate your right hand in the anti-clockwise manner. So your thumb points away from the section. This way, this one. So I would say in this fashion, T. Similarly, from the other side, you are rotating your hand in the you are rotating your right hand in the clockwise direction, T. So the thumb points away from the section. This is away from the section. So if your thumb is away from the section, so your torque applied or TMD would be negative. Torsional moment diagram is negative. So if you make that negative diagram, I would say there's some T downwards. Then after that, there is a torque that's in the same direction as we go from the x equals to 0 to x equals to L. If your arrow is in the same direction, that means you have to go to positive side. So if you move your trajectory from let's say from this side, if the arrows are finally in the same direction as that of traverse, if the direction of arrows is the same, then you have to increase the value. If the arrows are in the opposite direction, so you are moving in this direction. If the arrows comes in this way, you have to subtract that value. You have to go downwards by that amount. So we got this negative TMD, torsional moment diagram. So now the thing is that we have to derive that formula. Of torsion. Now we say that torsional formula. Before that, we had some assumptions. We need some assumptions. First one is that Hooke's law. That is stress proportional to strain. Next one is that shear stresses are maximum shear stresses are less than the permissible stresses. Maximum permissible stresses less than the tau max should be less than tau permissible, and we say that we use that. Our topic is that circular section. That circular section remains plane after twisting. So and if you use any other section, that would not remain plane. That don't remain plane. So that's why our goal is that we study only circular sections, and we use only circular section most of the time, because your other sections, they do not remain plane after twisting. They don't remain plane after twisting. They do show this property of warping. They show a property of warping. After that, one more assumption is that twisting couple is in plane perpendicular to shaft axis. This was your shaft axis, and the couple that the moment you develop that torque, that's developed because of that couple that's coupled because of the couple P1 P2 perpendicular to long axis, perpendicular to polar axis, I can say. As you can see from the first case, we say you are applying a load P here and a load P here, and such that you develop a moment of M T1 about the long axis. Similarly, you use the bracket plates in this way, or a bar in this way. Now you applied a load in the direction of Y, in the Y direction. So both loads, the combination of that, let's say this one is your PZ. So PZ, that's a couple, because we have two PZs and they are forming a couple, but that's perpendicular to the long axis. They are perpendicular to the polar axis. Similarly, your load in Y, that's also perpendicular to the long axis. So that's your next one. After that, you can say, let's derive the formula. So you have this section. Now you are doing one thing. Let's say this is your plane on which you have this shaft. You have the shaft here. And there is some length of L. The shaft is having some length of L. So there's some point O, that is the center. There's some point O at the center. Now you apply the torque. Let's say you apply the torque T. We say that this is your plane. This is your fixed plate. This is your plate the side on which your shaft is fixed. Now one thing is that you apply the torque T. Now what's happening? Let's take any element A. And if you have that in the cross section also along the long axis, I would say there is some point A here. If you join those, let's say this is your point A. And after you applied the torque, let's say the point A has shifted to some point A dash. Let's say it has reached to point A dash. So from this side, it won't go anywhere. Your point A would remain as it is. It won't, because your support is fixed. That means it won't allow that point A to go anywhere. This point A would remain fixed. A remain fixed from this side, but on the free side, we have the point A shifted to point A dash. So if you join it by a straight line, the phi here developed, here, that we call as angle of, or we can say shearing strain, or we can say distortion of that fiber. at that point, shearing strain. So it's the angle formed because of the torque applied, your A shifted to A dash, and the angle formed with respect to the fixed side. So you got this shearing strain. Now one more thing is that if you see the cross section, let's see the cross section. Your point A was at a distance of radius r. So point A was on the surface of the section. It was at a distance of r. Similarly, it has reached to some point A dash, but we said that plane section remains plane. Plane section remains plane. That means radius would remain as a radius itself. So it has shifted to some point A dash. So we say that there is some theta developed. We call it as a theta, and the theta, we say that that is called as angle of twist, or we say that that's angle of twist or angle of torque. Angle of twist or angle of torque. So we got two theta. One is your shearing strain. Phi. Next one is your theta, angle of twist. So it is similar to that. We have that beam. You applied a load P, and we have that deflection. We have that deflection of PL cubed by 3I. So that deflection, that's your transverse deflection, I say. That's your, because of that load, transverse deflection. And the strain developed, we say that the top fibers have tensile stresses, and bottom we have compressive stresses, because we have compressive strains here and we have tensile strains here. So strain is along the fibers. And this is your deflection, transverse deflection. Similarly, for this one, we have this one, that theta, that we can also call as torsional deflection. But your strain developed, that distortion of the member, that's your phi. So that's your distortion. That's your strain. Now we want to derive the formula for this one. So now if you analyze this figure, along any x-axis, let's take any cross section x-axis. If you take any cross section x-axis, and you take any element, let's take any element before that twisting. Let's say this was your element, this was your rectangular element here. You took the rectangular element here, a dash, between two lines. Let's say between two cross sections, you took an element of a dash that was rectangular, a dash that was rectangular. So this was before. So this is your A. Let's call it as area of, let's call it as alpha. So this was your alpha before, some cross section before. Then after the twisting has happened, so that fiber has reached somewhere here, that element has reached somewhere here. So this is after. This is after alpha dash. So if I say that alpha dash is, this is your alpha dash, that it is in this fashion, it has gone in this way. So I say that there is some development of shear strain. There's development of some shear strain. There is development of shear strain. Because of the shear strain, we can have development of shear stresses. We can have development of shear stresses because we have shear strain. So we can say there is shear stresses development. So now the thing is that we want to say influence, or we can say variation of your shearing strain. With the change in R. So you took that element A that was on the free surface, on the surface. So you took one element that was on the surface. Now if you want to take one more element that is at a distance of small r from the center. So if you take any point B dash that's at a distance of r from the center. So your r varies. If your r varies, we want to say what is the influence on the phi that gets developed. What is the variation of that phi? So for the point that was on the surface, we got a value of phi, maximum phi. We got value of maximum phi. We want to say on different values of r from the center, what is the value of phi at that location. So that's the variation of we call it as variation of shearing strain. Variation of shearing strain with change in r. That r is a point on cross section. That's a point P on cross section at a distance of r from center O. So let's have that diagram also. So we have this one. So this was your shaft, and this is your cross section. Let's say this is your cross section. Now you already took that element. Let's say this is the radius. Let's say this is the radius. Let's make this radius. Let's say this is the radius O, and you took the element A here, and it deforms to some, and it reaches somewhere to the A dash. It reaches to A dash. But the point A was at a distance of r. That's on the free surface. It was at a distance of r from the center. Now you took one more point. You take one more point. Let's have that. Let's connect to the first one. Let's connect to the first one. Then after that we can have. Let's connect the first one. Initially, the line of that A was this one, but the A has shifted to A dash. So if you join these two, we can have the value of that phi. I can write it as phi A. Shearing strain developed on that element A, phi A. Now if you take one more element, let's say this is theta. So if you take one more element on that same value of theta, if you take one more element at a distance of small r, let's say this is point B, at a distance of r, from the center. Let's say this is also r from the center. So this point has shifted to some B dash. It has shifted to some value of B dash. Now if you join those two along the long axis, let's say this is your B. And similarly this is your, and you have to show it in the cross section. Actually, you have to show it in the cross section. So you have to show it in the cross section. The line of the B would be in this way. Let's say this is your B. Actually, it should not be in this way. You should make, because it is a cross section, so you have to go just to the cross section. So this is the line that should be along the B dash. So I would say this is your phi B. The length L, we have this length L, and we have developed some triangles. If you analyze that, if you take that element, if you take that triangle, let's say the first triangle second triangle, that's phi for the phi B. So we have this length of L and phi B. We have this. Actually, the point B is somewhere here and somewhere here. So we have some circle. So let's say the circle is looks like in this way. So point B is somewhere here. Point B dash is somewhere here. Now let's say this is the small circle of radius r. Now if you say that this is some arc, how can you make a triangle, right angle triangle? But we say that this is triangle material, and phi value is very, very less. That's some value of 10 to the power minus 2 into some value of that 10, let's say 3 into 10 to the power minus 2 radian. That's very, very small. We say that the value, that circular arc is similar to that of that straight line. That because we're dealing with this form. If you take that assumption here and you solve that, you say tan phi B equals to, because your phi is smaller, I say that tan phi B equals to phi B. That equals to perpendicular by base, that BB dash by L. Similarly for the triangle, that because of phi A, I would write tan phi A equals to phi A, that is AA dash by L. I got these values. If you take now cross section, if you want to take the cross section now, your A was here and it reached to some A dash, so it was making an angle of theta. So this was theta. and this was radius r. What is the value of this one? What is the value of a dash? That's r theta. Similarly, you take the point B, it reaches to value of b dash. So this is your smaller value of bb dash equals to small value of r theta, small r theta. Now you got the values. You substitute here. bb dash equals to small r theta and divided by l. Similarly, your capital R theta by l. So we would say your shearing strain. I would say shearing strain. If you see that the shearing strain developed, shearing strain is equals to some r theta by l. So we got this value that shearing strain equals to r theta by l. So some value of r and some value of theta and some value of l. So we would say phi is a linear function of that radius. So as you move from the center, your shearing strain will increase. That means if you go to some point r at a distance of small r from the point or center, your shearing strain would be phi. And if you go to some value of capital R, your shearing strain would be maximum strain it can have, that is phi maximum. And if you go to the point r equals to 0, your phi would be 0. Then if you plot that variation, I would say your shearing strain would be developed in this way. This is your phi variation, shearing strain with the cross section. Let's say this is the cross section. I would say along this line, along these points, I would say shearing strain would be this one. Here the shearing strain would be this part, shearing strain 0. So this is the linear variation of shear strain along the cross section. Because your r is varying, your phi is also varying. So you got this one. Now we want to derive one thing from that. Now, if you use that Hooke's law, now, let's use that Hooke's law. Let's use that Hooke's law. What Hooke's law says? That stress proportional to strain. That means if you write shear stress proportional to shear strain, and we have tau equals to then some value of g into phi, where g is your modulus of rigidity. So if you want to say what is the value of tau now, what is the value of shear stress that is developed because of that element A became distorted because of some shearing strain phi. So I would say J, that equals to g times phi. The value of phi we derived, that comes some value of r theta by l. If you write that r theta by l, so your shear stress equals to g times r theta by l. If you want to plot that shear stress variation, then accordingly I would say, since your stress is proportional to strain and strain itself proportional to radius r, that means tau proportional to radius r, that means shear stress variation is also linear. Tau variation, that's also linear. So at some value of r from the center, we have some value of tau, and at some value of r max, we have some value of tau max. So we can say tau by r equals to tau max by r. So there is a linear variation. Now one more thing is that, so we got the value of tau equals to g times r theta by l. So if you want to say what is the value of tau max, tau max that equals to g times r theta max, we can say r theta by l, but r should be value of capital R. So r theta by l, that is also we can say g phi max, because phi shearing strain equals to some radius into theta by l. So this one is that arc length r theta, and you have that length of l. So you said that we have some triangle. So this is your r theta. Let's say this is your r theta and this is your length l. And we got the value of r theta by l. So final value, we can have that tau max equals to tau general value, tau at any value of radius r, with that equals to g times r theta by l. So we got one part of the formula. Now second thing is that you had that section, you applied a torque of T. Now to balance it, there should be some value of support. The support should resist it and give same value of moment. That should be in the anti-clockwise T. Now you take any section, cross section, you take any x-axis section, you analyze that section. You say, let's make that free body for that section. You say this is your section, first one, and this is your second one. You are applying a torque here. There should be someone to balance there. Let's call this as a resisting torque, internal torque. There should be some resisting torque. Similarly, from the other side, you are applying a T. There should be some resisting torque here. That should be, I think it is anti-clockwise. This one should be clockwise. T resisting. Now you want to say what is the value of resisting torque? So we say that T should be equals to T resisting. The torque you are applying, external torque, that should be equals to T resisting. Now you want to say what is the value of that resisting torque? So that the section here at the x section, that is resisting that torque. So if you take that section, let's make it a bigger. If you take that section, let's take a bigger section. Let's take a bigger section now. Let's take a bigger section. So this is your section. This is your x section. Now the thing is, you applied a torque of, let's say you applied a torque of T here, and the development of torque here would be some value of TR. Now similarly, if you take any section now, there should be some value of T resisting. That should be in the opposite direction. Let's say the direction of resisting torque. This was the long axis. I would say this was the long axis. This was the long axis in this way. So the torque is about the long axis. So if this is your resisting torque, that is contributed by the section itself. And how can the section resist? Because we have shear strain, and from that we have shear stresses. So we can say, because the shear stress is acting at some value of R, from radius, at some value of radius R from center O. So if you have that, that means if there is stress, that means there should be some force. If you take that differential element at any location, if you take any differential element of dA, and there is some shear stress on this tau, and I would say it's acting at some radius R, that means your force into R, that is your moment. So that can balance that resisting torque. That should be resisting torque integral. So we say that the direction, one thing is that we say the direction, this is one important thing here, the direction of shear stress tau that develops, is in the direction of torque itself. It is in the direction of, let's say that is called as resisting torque. That's in the direction of resisting torque. Now let's have this one. So if you take that, if you take any point, you want to say what is the value of tau here? I would say it's on the surface. The point is on the surface. Then that means at a distance of R from the center. The tau here would be tau max, and its direction would be tangential. So your tau is also tangential. One thing is that if your tau develops, that is not radial, that is tangential. That's not radial. It's not radial. Let's say that the tau here developed equals to some tau max on the surface. Similarly, if you take any point here, that would be tau max here, Similarly, here we have tau max. Similarly, somewhere here we have tau max. So that's along that tangential direction we have tau max. Now, if you take any element at a distance of R, we have that direction of tau would be in this direction, tau. And similarly, you take any element A, then the tau direction would be some value of tau. You take any element at a point at a radius of R, then the direction of tau would be tangential to that point, tau. Similarly, you take any point at a distance of R, we have the tau direction in this way. So tau is along the direction of that, direction of resisting torque. So we want to say, now we take that small element of dA, we take that small area of dA. This was your T resisting direction. We take some differential element of dA, and the torque direction, shear stress direction would be tau. Similarly, you take any element somewhere here. and the direction of tau would be in this way, tau at a distance of r. So each small dA contributes some value of tau at a distance of r. So if you say what should be the value of, I would write each dA, if I write the statement that each dA resists some torque of dtr, small torque of dtr, and that small dtr equals to that force into lever arm. Let's say the force equals to small shear stress, the shear stress developed at that location of r, and I would say tau into dA, smaller force of tau dA, and the length and that radius point from the center, that's equals to r. So we got this value of shear stress and that resisting torque. If you say what is the total value of that dtr, that would be equals to tr, that equals to integral. The value of r should be from 0 to some value of r max to some value of r. So I would say 0 to some value of r. So that's tau dA r, or we can write r tau dA. But we have the equation that we got the shear stresses. We got the shear stress equation earlier. Shear stress equation that tau equals to gr theta by L, and at any location we have tau equals to gr theta by L, because your r can vary. This capital R is the r max. This is the r max, so that we have tau max. But we have that any general value of tau at location of small r, so we can write gr theta by L. So let's write that. That is integral 0 to r times gr theta by L and dA. Now if you see that, what is this? If you solve it, we say that there is some g theta by L, and we have integral 0 to r square dA. And what's this second moment of area? What is the second moment of area? We call it as, moment of inertia. That we call as a moment of inertia. But the thing is that the rotation is that we have this section. This section is in the z direction and in the y direction. So we have the section of, we can say z in the zy plane. Section is in the zy plane. But rotation is about the long axis. So we have this section. Let's say we have this section. This is the long axis, polar axis. Our long axis, we can say long axis or x-axis. The rotation is about this axis. Rotation is about this axis. So there should be some resistance in that axis that can resist to this rotation. Actually, what is the value of what do you mean by that value of I? What do you mean by moment of inertia? Actually, where it helps? So you are applying some moment. You are applying some moment in the direction of mx. You are applying a moment of m in the z direction. You say that the value of I was equals to bdq by 12. Actually, it was about the zz axis, that neutral axis. Izz. We said that Izz is equals to bdq by 12. So because of that moment mz, that moment is about the z axis, there should be some resistance. There should be some resistance to rotation, because moment produces rotation, 1 by r, curvature, bending. So because your moment produces resistance, rotation, we say that there should be some resistance to rotation. That is because of that moment of inertia that resists this rotation in that axis, about that axis. Let's say you are applying moment in z direction, so you say that bdq by 12 because of that Izz. We have that sigma by y equals to mz by Izz. Now similarly, you applied a moment in y direction, my. You applied a moment in my. So we said that this is your bdq by 12. Then we said that moment applied in y direction, there should be some resistance. So we said that let's take Iyy. That's dbq by 12. So there should be resistance in that same direction. Now for the torsion case, you have the section in the zy plane, but the rotation is about the x plane. But the rotation is about the x direction. Rotation is about the polar axis. There should be some moment of inertia about that polar axis. So we can say that this moment of inertia is about the polar axis. This is moment of inertia about the polar axis, or long axis. That we call it as a polar moment of inertia. Polar moment of inertia. So it's out of the plane. So this r is out of the plane. So actually you are going to some point of r. You are going to some point of r. This is r. You are going to some point of r in the space. At its distance of x from the, let's say at a distance of z from the point center, and at a distance of y from the center in the y direction. So at a distance of z comma y in the space, you have this point r, point P, you have this point P at a distance of r, radial distance, but it's in the space that is out of the plane. So you have that section zy is out, that bending is out, that moment is applied out of the plane. I can write here, moment applied is out of the plane. Moment m, x, that's torsion, that's out of the plane. So there should be some integral y r square dA that is out of the plane. That's out of the plane. That we call as polar moment of inertia. That is J. We represent it as a J, and that is equals to summation of the moment of inertia in two directions. Let's say Izz plus Iyy. Izz plus Iyy. Because your section, we say you go to some value of r that's at a distance of z from the center in the z direction, and at a distance of y from the center in the y direction. So you go to some point P. So it's contributed by two inertia about the section. So if you write that, I would say that's equals to y squared dA 0 to some value of y max, and similarly integral 0 to, let's forget the limits, and similarly z squared dA Izz plus Iyy, and that's equals to some integral z square plus y square dA, that's also equals to some r square dA, and that we called as J. That's polar moment of inertia. Now we know that if you have this what we call as circular section, we have that moment of inertia all principal planes. That means moment of inertia about any x is equals to pi d power 4 by 64. Either you write I y, you write I z, that is same. Then J would be equals to 2 times pi d 4 by 64. So let's have that. So we got the equation now. We got the equation. If you zoom in out, I would say we got this value of g theta by r, g theta by l. So finally we got some value of t resisting, and that should be some value of t that equals to g theta by lj. So we got this equation. The torque equals to g theta by l into j. Now if you write the final equation, that final torsion formula, we write in this fashion, that in the fashion of flexural formula. We have the flexural formula, that sigma by y equals to m by I equals to E by R. In the same manner, we write shear stress by at a distance of r. Similarly, bending stress at some y from the neutral axis, at some point y from the neutral axis, bending stresses, and the bending stresses were in this fashion. And we say that shear stress is because of the torsion at some location of r from the center, that equals to tau by r, and the variation is also same in this way, or you can share in this way. So we have the shear stresses tau by r equals to moment, you have m by I, you have here torsional moment t by, there we have moment of inertia, here we have polar moment of inertia j, and there we have E by r, that means we have here g, and for the r we have here theta by l, because we know from that we have that length of l. This is actually the phi. This is your actually that r theta by l. If you write here, we have this E by r, and here we have theta by l. Actually, we know that r theta equals to l. If you have some r, and add a theta, So we can write this is some length of L r theta. So L equals to r theta. Similarly, for the torsion, we write in terms of theta by L. We write in terms of theta by L. Theta by L. G theta by L. G theta by L. So we got this equation now. Final equation that tau by r, T by J, G theta by L. This is your torsion formula. That you also can write that tau max by r max equals to this one. So we got this equation. We got this equation. Finally, we got this equation now. What should we do? What should we do now? Now, if you want to plot the variation, we said that the shear stresses. This was your section. This was your section, and there was some resisting torque D. There was some resisting torque TR, and we say that the shear stress variation is the tau is in the direction of in the direction of TR. That's tangential. Tangential. So at every point, this is tangential in the direction of TR. If it had been radial, let's say it was radial, so each point would have each shear stress would get cancelled out from each other. So there was an unbalance of that TR, so it would rotate. So there is an acceleration, I can say, angular acceleration of that section. So the tau developed is the tangential tau. So we got this tau, and it's maximum at the surface. That means if you go to some point r, you have tau max, and if you go to some value of small r, you have smaller value of tau, and direction is also in the same direction. That's tangential to the surface. So if you have that variation, that's the linear variation of r. So if you have that linear variation of r, I would say this is the shear stress variation. This is the shear stress variation along the length. So here we have 0. Similarly, from the bottom side, we have tau max here. We have some tau max here. We have some tau max here. We have some tau max here. So I would say along this length, your tau max is in this direction, tau max. Then after that, at some point, there we have smaller tau. After that, we have a few smaller one more tau. Then after that, it goes decreasing, decreasing, decreasing. Now, if you plot that, if you have that triangle, I would say this is our variation. You can show final variation somewhat in this fashion. That final variation of the shear stresses for this case, that if the torque is anti-clockwise, I would say. If the resisting torque is in this fashion, then I can show the direction of arrows in this way. So this is your T resisting. Because of that, I would say this is your tau variation. Then after that, you go downwards. You go to the bottom side of this. You go to the bottom side. I would say this is the variation tau. Then finally, we say that this is the variation tau. This is the variation that this is straight. Then after that, at the end, this is straight. Then there is a linear variation. So this is the variation, actual variation, shear stresses. Now, if the torque was opposite, if the torque, resisting torque was in this direction, then I would say this is the variation. This is the variation tau. This is the tau variation. Then similarly, you can this equation we have. This is valid for the. This was the case for, I would say, that's called as solid circular section. Solid circular section. Now, if you take hollow section also, let's say this is hollow section. Let's say this is the section, and this part is open. This is hollow. So we have the section. This is your section, hollow section, and shear stress variation is same as that of. That means we can show the shear stress variation tau. This was your T resisting. That means the tau would be varying in this fashion. Let's say this is your material up to the hollow part. Then here we have free surface. Here we have free surface. So we say there is some tau max here, tangential to that. Let's say this is some tau max, and it will linearly vary to. It should have been 0 to the point of center, that r equals to 0. But we have smaller r minimum. We have r minimum equals to some value of some inner diameter by 2. So we don't have r minimum equals to 0. But for the solid circular section, we say that r minimum equals to 0. But for this case, we have r minimum equals to di by 2. So So there would be some minimum shear stress. Here the minimum shear stress was tau minimum equals to 0. But here would be some tau minimum shear stress because we don't have in the hollow part, because we have a hollow part there, we have shear stress is 0. That means we don't have that material there. So because of that, we have some minimum shear stresses also here. Let's say the shear stresses here is tau minimum, I can write, and this is tau max, and it's linearly varying. It's linearly varying shear stresses. Similarly, from the other side, there's some minimum shear stress, then after that tau max, and there's linear variation. So this is for the hollow section. And you can take any other section also. Let's say let's say this was section, this was hollow. If you take along this line, we know that tau would be tangential to that. That means if this was your resisting torque, that means tau would be in this fashion, and there would be some minimum value. So you join those two. Similarly, from the other side, there is some tau minimum and tau maximum in this fashion. So this is your tau variation. So we got this now. Let's talk about the pure shear case. Let's talk about the pure shear case. Pure shear case. Let's say what is the pure shear case saying? Because of pure torsion, pure torsion, no bending moment, no axial force. We have only pure torsional moment diagram, and we say that because of tau we got some shear stress. Because we got some value of phi, because of that we got some value of shear stress. So we write that tau by r t by j g theta by l. Now you want to say what is pure shear here, because we say that you applied a torque and there is development of shear. Now if you take that element shear, that's positive shear stress tau, you want to say what is the value of maximum normal stress. What is the value of maximum normal stress? That's major principal stress and minor principal stress, I would say. Sigma 1, sigma 2. We know that sigma 1 and sigma 2 equals to sigma x plus sigma y by 2 plus minus root of that radius square. But for this case, pure shear, we have sigma x, sigma y 0. Then we are only left with that radius. Let's have that radius. That root of sigma x minus sigma y by 2 whole square plus tau xy whole square. Let's say this is some tau. Let's say this is some tau square. So this is also 0. So we are left with that sigma 1 equals to plus tau and sigma 2 equals to minus tau, and that are equal that at a location of tan 2 theta p equals to 2 tau xy by sigma x minus sigma y. So some infinite. That means theta phi equals to at 45 degrees. At 45 degrees principal plane. So at 45 degrees we have some principal plane. This is some sigma 1. And this is some sigma 2 compressive. One is tensile, second one is your compressive. Sigma 1. This is some sigma 1 and this is some compressive sigma 2. That is tau and this is minus tau. So if you write that, what is the value of normal strain? If you write what is the value of normal strain? Do you know what is the value of normal strain? Normal strain. If you write maximum, if I write normal strain, if I write normal strain, maximum value. What is the value of maximum normal strain we can have? That we call as major principal strain, E1, that is sigma 1 minus mu sigma 2 divided by E. If I write that sigma 1 is plus tau and minus mu sigma 2 is minus tau divided by E. So we got value of tau by E1 plus mu. This is your normal strain, maximum normal strain we can get. That we also call as major principal strain. Do we get this? Do we get this? Now, if I use that second equation of that normal strain, we have that E1 equals to EX plus EY by 2 plus minus root of EX minus EY by 2 whole square plus some gamma XY by 2 whole square. So if I write gamma in terms of phi, because we are dealing with phi now, we take the phi as the shearing strain. If I write that phi XY by 2, so I say that strain, I would say that because the strain is in x and y, because I would say the thing is that we have already discussed about that, because tau and sigma are independent of each other, because shear stresses produces only shearing strains. It does not have any effect on normal strains. It does not have any effect on normal strains. So because of that, because of the loading that you are applying at torque, because of that we have shear stresses developed. So we have normal stresses equals to 0. So the normal stresses we have 0. That normal strains we have 0. Normal strains we have 0 because of the loading. This one and this one is we have 0. So your maximum normal strain we can get, that is major principal strain, that equals to 5/2. I would say that equals to 5/2. So the conclusion is that for the pure shear, or we can say for the pure torsion, your major normal strain, maximum normal strain equals to that shearing strain by 2. Shearing strain by 2. So this is one important point here we get. So if you have these two equations, that if I write that, I would write phi by 2 equals to tau by E 1 plus mu. So we got these two from the two equations. We got the result here. Now if I analyze it, if I write that Hooke's law equals to tau g phi. So if I write tau by phi, that is equals to tau by phi, that equals to 2 by E tau by phi. Yeah, that equals to E by 2 1 plus mu. So what's the value of tau by g? Tau by phi, that's g. That's g. So we got a value of E equals to 2g 1 plus mu. So this is the derivation of that relation between the two elastic constants. E equals to 2g 1 plus mu. So one more thing is that how can you get the value of g? How can you get the value of g? So we have that equation that tau by r equals to t by j equals to g theta by L. Now you have some shaft, you are doing torsion test. So what's happening here? We have some length L, we have some cross section of diameter d. So you are doing torsion test. Let's say torsion test, you are applying a torsion of t, torsion moment of t, and let's say it's gradual. So you are applying t. Based on that, we have some deformation of phi, shearing strain. So if you use this part of the equation, I would say if you have that t versus phi plot, or I can say t versus theta plot. If I have this t versus theta plot, if I write that t by theta equals to gj by L, that equals to gj by L. That means if I have the initial linear portion, because we are dealing with the SOM, that's the elastic part, we can have some linear curve in the first part of that t versus theta. We can have some value of alpha here. So I can write tan alpha equals to some value of t by theta. And if I use that, I will write tan alpha and L by j equals to g. So I got a value of that. How much value of g is there for this particular material of length L and diameter d. So I can get the value of L by j into tan alpha. We are dealing in SOM, so we can say there would be a linear variation initially. And you take that part and you get the value of g. So that was the determination of g. That was the determination of g using torsion test. Hope you enjoyed this part of the lecture. Next topic for this chapter is that if you have the shafts, they are placed in the series. We have shafts placed in series. So let's say this is your shaft 1 and there is your shaft 2. We have L1, G1, J1. We have L2, G2, J2. Now you applied a torque here, T. Let's say from this side it's fixed. You applied a T here. I would say that from the free body diagram, I would say you're applying a torque T here. T. let's make the line diagram first, then after that it becomes easier. Oh no. Let's say that you make line diagram. So you're applying a T here, and you use the right hand thumb rule. You're applying a T clockwise. That means the thumb is pointing towards the cross section. So you can show there that is T, and based on this you can say the direction developed here would be the direction developed here would be anti-clockwise T. Anti-clockwise T, that means pointing towards the thumb, pointing towards the section. So that's some T. So now you don't know the value of what is the value of J here? What is the value of G torque here on the junction of two? Based on the concept that we have series connection, we can say directly that the tau would be same for the two. Let's still make the free body diagram. Let's make the free body diagrams. So this is your torque. You are applying a torque of T, or we can make from the line also. We can make from the line itself. So let's say this is some line. You're applying a T here. There should be some balancing T, and similarly from this side there should be some T here on this side there. This is also T. So this is the balancing of that free body diagram. Let's say that how much theta is developed. How much theta it develops. We know that theta equals to T L by Gj, based on this equation that T by J equals to G theta by L. So we have that. The question is that get the total theta of that combination of those shafts. Theta total. I would say theta total. I would say here we have, let's call it as A, B, C. I can say theta at A equals to 0. And if I calculate theta at C with respect to A, that I can say because of the torques in the individual shafts, I would say that's contributing some small theta values of, let's say, theta C with respect to B plus theta B with respect to A. If I calculate those two values, I would say theta equals to TL by GJ, and for this part ABC, for the BC part, I would say that is some torque T, some length L2 by some value of G2 and J2 plus. Similarly, you have theta B. Both values are positive. If you see, this one is some positive value T, and after that you have one more T. So there is a T that's constant. So positive, you can have that positive T in the both ones. So T L1 by G1 J1. So you got this one, total theta. Theta at, we can say finally this is theta C also. Now if you take problem 1, let's take problem. Let's say that you have the shaft of length 3L. Let's say this is A, B, C, equally spaced A, B, C, D. You applied a torque of T here about the polar axis, and you applied an anti-clockwise T, 2T here, and you applied 3T clockwise. This is 3T. Now if you take line diagram, let's have that line diagram. This is line diagram. So your T is clockwise, that means thumb points towards the cross section. Thumb points towards the cross section. Thumb points towards the cross section. This is some T. After that, you have anti-clockwise T, 2T. Anti-clockwise 2T, that means away outwards in this way, 2T. This is 2T. And after that, you have clockwise 3T, that means in this way, 3T. And there should be some net value of these three. I would say 3T is in this direction. Then we have minus 2T in this direction. Then we have plus T in this direction. So we got a final value of 4 minus 2. We got some net value of 2T in this direction. So there should be some balancing 2T at A. T at A should be equals to 2T in this direction. So let's have that. Let's say this is some TA equals to 2T. So now if you want to make that torsional moment diagram, I would say there is some T TA equals to 2T positive, some positive 2T. Then after that it is straight, it remains straight. This is torsional moment diagram. This is moment diagram. Then after that you have 3T in the opposite direction. That means you have to go that final value I can write M2 minus M1 equals to M external applied. So I would say your next moment M2 would be equals to M external minus plus M1. So your M1, M external, you applied 3t, anti-clockwise, minus negative, I can say negative sign, and plus M1 was your 2t, so net value of minus t, minus t. Then after that, it will remain same, and there is an increase 2t. So your net value will increase. So minus t plus 2t, net value of t. After that, you have this one. So this is your torsional moment diagram. So you have this torsional moment diagram, and the lengths we have same, L, L, L. G is also same, J is also same. So if we say what is the total value of theta, I would say total value of theta equals to 2t L by Gj plus minus times TL by Gj plus TL by Gj, because your T is here negative. So that will rotate this part, BC part, in the opposite manner with respect to the part AB and CD. Negative means it would rotate, let's say these two rotate in the clockwise manner, and the part BC would rotate in the anti-clockwise manner. This is the meaning of this one. Now we got the net value of theta equals to theta at D, that equals to theta at D with respect to A, that is theta D with respect to C plus theta C with respect to B plus theta B with respect to A. And we got net value of theta equals to 2TL by Gj, 2TL by Gj, 2TL by Gj. And from this one, from the torsional moment diagram, we said that the maximum moment developed here would be 2T. So the critical for design, so this part is critical for design. If you design AB, if your design for AB is safe, that means the rest of the part is safe also, because your torque developed here is maximum 2T. Now take one more that we can say. If you want to say what the from the equation we have that here the shear stresses would be maximum tau max, and if you use that equation, tau max by R equals to T by J. If you use this equation, and what if you say what is the value of J? Value of J is equals to we know that value of I equals to pi d power 4 by 64. Let's say I and similarly IZ equals to pi d power 4 by 64. If you write now J is the summation of 2, that means pi d power 4 by 32. So this is your J. If you substitute here value of J, that means T by pi d power 4 by 32. So what is the value of R? Maximum value of R we can have, that is diameter by 2. So you have that, you have the final equation that tau max equals to 16 T upon pi d cube. So this is your maximum shear stress developed because of the torsion, tau max developed, maximum shear stress developed is equals to 16 D by pi d cube, and the variation of shear stresses is in this way. Let's say this is the variation based on the direction that this is resisting torque. So if we compare the shear stresses because of torsion, tau because of torsion, with respect to the tau because of the unbalanced bending forces, we have that unbalanced bending forces Fxx and Fyy because of My by I dA integral. So we got some value of F, that was tau T dx. So there was some shear stresses, and we said that the shear stress variation is a parabolic variation. So this was because of bending forces, or we can say because of shear, because of transverse shear. So shear stress variation here is some parabolic, and because of torsion we have shear stress variation, that's a linear variation. So keep that also in mind. So we have two shear stresses. One is your direct shear stress, we call that, and next one is your indirect because of the torsion. One is your linear variation, next one is your parabolic variation. And see also that maximum here we have at the center we have 0, and here we have maximum at the mid. Now one more thing is that so we got this value of tau max, maximum shear stresses, that can be designed if you know that material. Say if you select some material that has some maximum capacity of tau max, it can allow as that of steel we have that Fy by root 3, that is 0.57 Fy. So maximum it can allow in the uniaxial tension this much. Similarly, if you know that material of some value of tau max, and you are applying a torque of T, and you can say what should be the diameter I can use for this material, so that the material will not have the stresses greater than tau max. I want that tau should be less than tau max. For that, you should increase the diameter. You should increase the diameter such that your torque is satisfied. Okay. So you have to accordingly change the diameter also. So got the tau max. Similarly, from the bending stress formula, we have sigma by y equals to m by I. And if I write the sigma max, I have to write here m max. I have to write here y max also. And this is neutral axis. So you have that circular section. What is the value of sigma max I can have? If you go from y max equals to d by 2, if I write that m by, we know that I equals to pi d 4 by 64, and we have d by 2 maximum. So we got value of 32 m by pi d cube, sigma max. So shear stress equals to 16 t by pi d cube, and this one is your 32 m by pi d cube. And these two we can use that when we studied next topic of that is called as combined stresses. Then we use those two values, combined stresses. Now let's take the problem of statically indeterminate problem. Statically indeterminate shafts. So we have this one. So you are applying, this is length L, this is 2L, then this is length L. Now you are applying a torque here equals to 4T, and you are applying clockwise torque here equals to 2T. Now you want to say what's the different in the different parts of that shaft A, B, C, D, what is the value of that torque by the torsional moment diagram, and accordingly you can get the value of theta, total theta, and theta at any location I. So if you say what is the by the compatibility, can you say from the compatibility equation that theta A equals to theta D equals to theta at A with respect to D, that is also 0, and we can also say theta at D with respect to A, that's also 0. So that means summation of all those theta would be equals to 0. The torque would be contributed between the three spans in such a way such that net value of theta would be 0. This should be satisfied. And we can also make the line diagram. Let's say that we have clockwise 2T, clockwise. Yeah, this is anti-clockwise. Actually, it should be clockwise. Let's say this is clockwise. This is the clockwise 2T. That means it is in this way, 2T clockwise, 2T. And this one is your anti-clockwise. I have made some problems here. 2T. Let's make that problem in new fashion. Let's say that. Let's make the problem in this fashion. So this is your side fixed, and this one is also fixed side. So you're applying a torque of, let's say this one is your clockwise, let's say this is your clockwise 2T, and this one is your anti-clockwise. This one is your anti-clockwise. This is your clockwise. Is this clockwise? No, this is not clockwise. This is anti-clockwise. So for the clockwise, you have to show arrow in this way. So this is clockwise 2T. Let's say this is your section. So for this one, you are applying 2T here and anti-clockwise. यार कमजोर हो गए. Let's say this is your clockwise. Okay. Yeah, this is clockwise. Let's say this is 2T. After that, we have anti-clockwise 4T. Anti-clockwise 4T. In this way. Yeah, we have this 4T. In this way. This is 4T. So this is your section. So this is your section, L to L and L. Let's call them as ABCD, ABCD, ABCD. So we have the strain compatibility equation also, that theta at ends equals to 0. Now if you want to say from the line diagram, if you make the line diagram, let's make the line diagram. I would say there is a clockwise moment. Yeah, this one should be anti-clockwise. This one is anti-clockwise in this fashion, in this way. This is anti-clockwise 40. So you are applying clockwise moment here 2t. So this is clockwise. OMG. This one is anti-clock. This one is clockwise. Sorry. Finally, you got this clockwise in this fashion. That this is clockwise. This is clockwise, and anti-clockwise should be anti-clock. This one is anti-clockwise. Anti-clockwise. This one is anti-clockwise. Confusing by. This one is, what is this about this axis? This is anti-clockwise 40 and 2t. You have to show clockwise. Is this anti-clockwise? Confusion right? 40. Let's wait for some time. And let's go get those theta. So we had that. Finally I can show you that this is your beam, this is your shaft of length 4L, and fix it on the sides A and D. This is side A, this is side D, and length L to L and L. This is point ABCD. Now you're applying a clockwise torque. Clockwise torque. That means in this fashion. Clockwise torque. This is not clockwise. About this long, I would say this is clock. This is anti-clockwise. So finally, you are applying a torque of 2t here. 2t clockwise, and at this point, you are applying 40 in the anti-clockwise. Let's make the line diagram now. For this one, arrow should be in this way. This is your clockwise. About this axis, clockwise. So if you want to make the clockwise, that line from the line diagram, if you want to make line diagram, so you're rotating that clockwise. That means arrow thumb points towards the point support A. So thumb points towards the support A. This is 2t, and you're applying anti-clockwise 40. That means anti-clockwise 40. That means thumb points towards support T, 40. Let's say this is 40. Now I can say there is some net value of 40 in this direction minus 2t in the opposite direction. So net value of 2t in this direction. So if I say to balance this net, there should be some opposing moment at the A. Let's call it as a TA. So there should be some TA in this direction, and there should be some TD also in the same direction, TD. So that they balance that 2t. Let's write that TA plus TD equals 2t. TA plus TD equals to 2t. That means if you substitute these in terms of 1, I can write, let's say TD equals to 2t minus TA. TD equals to 2t minus TA. If you make the free body diagram, or you can say if you make the actual those torsional moment diagram also, I would say you are going in this fashion. Your traverse is in this direction, but you are facing a TA that's in the opposite direction. So TA is negative here, negative TA. Then after that, after this point, there is an increase of 40. Then I can say this is some value of 40. Let's say the value increase it to some value of 40. Let's say this is 40 minus TA. Net value of some 40 minus TA, because we want, if you go to the positive side, that means 40 should be more. That means 40 should be more than TA. So if this is positive, that means let's go to some value of 40 minus TA. if you want to say it was some value of TA minus 40, then you have to go only below the line. So this was some TA minus 40, this one. You should have gone in this way. If you go to the value of 40 minus TA, that means you have to show out on the top, that positive side of the diagram. 40 minus TA, then after that there is a 2t decrease, then finally it would become 2t minus TA. Then after that constant, and after that it would decrease because your TD is in the opposite direction. So this is TD equals to 2t minus TA. And if you see from the diagrams also, that this is also satisfied. So this is correct. So TD equals to 2t minus TA. Now one thing is that we know the compatibility. We have the compatibility condition. That total theta, I can say that compatibility equation, that theta A equals to theta B equals to, theta A equals to theta D, that equals to theta A with respect to D, theta D with respect to A, that equals to 0. You can go from either of the sides. I can say theta D with respect to C plus theta C with respect to B plus theta B with respect to A, that equals to 0. Now you substitute the values of different D, theta equals to TL by GJ. You substitute those values. Your J and G is same. Your J and G is same. So I would write 1 by GJ as common, and length we have length also. Length is varying, and your, let's say for the CD, for the part CD, your torque equals to 2t minus TA. Your torque of positive 2t minus TA. Your positive torque of 2t minus TA for the length of L, and plus, and this was positive. And after that, for the theta CB, you have positive torque value of 40 minus TA for the length of 2L, and divided by GJ plus. After that, for the part AB, you have negative torque. Of minus TA, minus TA, and length is L, length of L, divided by GJ, that we have common, so equals to 0. So finally you have this equation. You can get the value of TA. I can write 2t minus TA plus 4t, minus plus 8t minus 2t minus 2TA minus TA equals to 0. So that means 2 plus 8, that is 10t, equals to 2, 3, 4, 4t A. That means T equals to 2.5 of torque T. That means 2.5 T. That means the direction you assumed is correct. That means the direction of that torque at A, that is in this direction, negative torque, I can say. Out of the, that's facing outward, away from the section. This is section, it's facing away from the section. So T is negative. So 2.5 torque. Then after that, if you want to say what is the value of torque at the D, that value equals to 2t minus 2a, 2t minus ta, 2t minus ta. So net value of minus 0.5 t. That means the direction you assumed the direction of td in this direction. So final value of td is in this direction. So that's also negative because it is facing away from the section. So td is also negative. That means net value of td equals to 0.5 t in this direction. So final line diagram should look like now. If you want to make the final line diagram, I would say your TA is positive. That means the direction you assumed initially, that is in this direction. That is correct. So TA is in this direction. So TA 2.5 T in this direction. After that you have 4T. You have 4T here, and after that you have 2T, and finally you have you assumed that TD is in this direction, but you got TD negative. That means the net value of TD is in opposite direction, that is in this direction. So you have to say this is 0.5 T. And if you want to make the final torsional moment diagram, you can make that also. So let's say this is the reference line. You can say you have negative T. You are going from, say, from 0 to some positive x, and you are facing a torque that is in the opposite direction. So minus 2.5 T, then after that constant up to this point, and your torque increases because you are moving in this direction, and torque is also increasing in this, and torque applied is also in the same direction. So increase final value would be 4 minus 2.5, that is 1.5 t. After that you decrease it by a value of 2, then finally you can get minus 0.5, minus 0.5 t. After that it will remain constant, and your direction of arrow is in the same direction of your traverse. That means you have to increase it by 0.5 t. So this is your negative, this is positive, negative, positive. This is torsional moment diagram, TMD. So you got this one now. Now if you want to say, if you want to talk about, if you want to talk about that particular theta, I had named them as A, B, C, D. If you want to say what is the theta developed at C, because the ends are supporters, and supporters are fixed, so there should be some theta in the individual members such that the net value, final value would be 0. If you say what is the value of theta C, so if you talk about theta C, I would say either you can talk about in this way, or you can talk about in this way. I can say theta C is equals to theta C with respect to D, or you can say, or you can go in the opposite direction. You can say theta C with respect to B plus theta B with respect to A. You can have these, but there might be chance of that sign would be negative for the one. So you can say mod of one would be equals to mod of other, such that net value would be equals to 0. So if you say theta C D plus theta C B plus theta B D, if you actually, we know that actual value equals to 0. If you sum them, let's say this, you got some value of theta C with respect to D, plus you got some value of theta CB plus theta B with respect to A. You got some value. If you subtract them, you could get value of 0. So let's forget that. If you want to say what is the value of theta CD, you have to take TL by GJ. But for that, you have to take T because of this one. So you have to write minus 0.5 T length of L by GJ. So you got a value of minus 0.5 TL by GJ. So you got this moment of T 0. You got this value of theta equals to 0.5 minus 0.5 TL by GJ. And if you want to say from this side, if you want to calculate theta C, from the other side, if you want to say, so theta C, if I write theta C with respect to, from this side, I would write that equals to theta B with respect to, theta C with respect to B plus theta B with respect to A. This part and this part contributes to the theta at C. So theta C with respect to B, for that you have torque of 1.5 T. 1.5 T, length of 2L by GJ, that's positive torque. And similarly for the next part, we have negative torque of minus 2.5 T and length of L by GJ. So you got a net value of 3 minus 2.5, that's positive 0.5 TL by GJ. So you got from this value positive, and initially this one was negative. That means from this side you have negative, and from the other side you have positive. If you add them, if you add all those, you could get a value of negative. You would get a value of 0. That means that is the compatibility equation. That is the summation of all the theta between the 2 points A and B, A and D, that is equals to 0. Similarly, you can calculate theta B also. Theta B would be equals to only this part, theta BA. So theta B would be only equals to this part, 2.5 TL by GJ. From this side you got negative. From the other side, if you go, you can get a value of 2.5 TL by GJ. TL by GJ. Hope you understood the problem. Let's take one more problem, that you have this shaft between the two fixed ends, fixed supports, and you have this length A, this length B, such that A plus B equals to L, and you are applying a torque somewhere at A from other side and B from other support. And you want to say what's the different values of those supports, how much torque each support resists. Let's say you're applying a clockwise torque. That means your thumb points towards support A. Let's say that this is support A, this is support B. So you're applying torque at C. So I would say a torque applied at C, it is in this direction. Thumb is in this direction. So I can write that let's say this is net torque of T in this direction. So I would say there would be some torque A at A in this direction, and there would be some torque B, let's say in this direction, such that I would write TA plus TB equals to T. So let's say there is some torque at A, TA, and there's some torque developed at B, that is TB. Now, if you want to make the diagram TMD, I would say you go in this direction, and your arrow is also in the same direction, so your TA is positive TA. After that, you decrease it. You decrease it there. Let's say you decrease me there. You decrease me there. That means you got a value of T minus TA here. And finally, your value stops to TB. That is also T minus TA. Now you want to say, by using the compatibility condition, that theta A equals to theta B equals to theta B with respect to A, that is theta A with respect to B, that equals to 0. And that equals to theta at B with respect to C plus theta at C with respect to A. Now for those, you have this positive negative, so you can write what is the value of theta B? Theta B with respect to C, that means this part you have to contribute. Theta B with respect to C, I would say that is equals to torque of T minus TA and length of B, because length is B for this part, and divided by Gj plus, and this was negative moment, actually this is the negative torque, so finally you can write minus times this torque and plus positive times this torque for the theta Ca, that is TA and length of A by Gj, and that should be equals to 0. That should be equals to 0. So you got a value of minus T minus TB minus TB plus TAB. Yeah, this is not TAB, that is T at A into B, that is T at A into B, then plus T at A into A equals to 0. So you got a value of TA, A plus B equals to T times B. So you got a value of that torque resisted by developed at A equals to T times B by L, or you can write T B A plus TB by A. As you know that for the simply support beam, you're applying a load of P at a distance of A and B. So you say, what is the reaction developed here? We would say the reaction developed would be equals to P B by L, and here the reaction would be P A by L, because you're taking moments about the opposite side. If you take moments here, you have to multiply a length of A into B for this reaction. I would say reaction of A into B, that should be balanced by P into opposite side. P into opposite side, that's A. So you're taking moments about A, and you get reaction of B. That means this is reaction of B. This is reaction of B, and in the reaction of B, you got the opposite side, that's A. Similarly, for the moments at A, if you take moments about B, you got A into, this is some reaction, A into A plus B, that's P into B, P into B. So you got for A, you have opposite side B. Similarly, for the moments, you have the moments P, P, A, B, by L. Let's forget moments, P, A, B by L. So you got this. Similarly, you have this one, TB by L. Similarly, if you want to say what is the value of TA, TB, that's equals to T times A by L. So that's the end of this chapter. I would say this is the end of this lecture. Thank you for watching this series by Concrete Path.